All right, settle down, class. Settle down. Talking to you. Yeah. All right. So, what we're going to do today is we're going to do, a video lesson. It's going to be on the Bohr model, and then on Lewis models or Lewis dot structures, then a little bit of the bonding at the end. We are going to do some of the homework, so I'll help you with that. Some of it I am going to skip over because we're kind of just going to get into like the bare bones of it. I am going to touch on it a little bit. What this first part was going to ask you to do is draw some models of the atom. And if you turn to this page, what you should be seeing, or what you'll probably have, is some things like this, right? If you remember, we have our Jimmy Neutron model, right, or the Rutherford. This is talking about orbitals, right? So this should be a little bit more familiar to us. What else? We don't really have like a plum pudding or anything. No, we kind of have the Bohr. We have the Bohr model here, which is going to be the one we're going to touch on. So we know none of these are actually the way it looks, and we said that. But for now, it is going to be okay for us to think about it like this. And this should be familiar to you. Nucleus. Remember, this is not to scale at all. Center should have, well, it makes up most of our mass, but we have our protons and neutrons, and then we have rings around it, and those are, remember, supposed to be our orbitals. Remember, this is the Bohr model. Remember, we said it was Bohr ring because it wasn't all cool like this one. We just had our very standard and perfect circles around our nucleus here. For this way of thinking about the atom, it's actually really effective for the bonding and things like that. We're going to get into why at the end. So here's a picture of Niels Bohr and Einstein just chilling. So that was probably maybe around the 1930s, I believe. So this should all be fairly familiar to you guys. Okay, so what that previous one was showing was a picture of carbon, and I'm not sure why the light is not that good on this. I just kind of messed everything up, it seems, but I think we'll be fine. So carbon, we know we have our atomic number right here. We have our atomic mass. Remember, this is going to be the one that we're going to care about for this. So here we have 6 protons, which means if it's neutral, we should also have 6 electrons. All right. You should be familiar with this. You should have seen this before. But why? Why do we know it's set up like this, where we have 2 rings, right? Where the first ring has 2, the second ring is going to have 4. We know in total we need 6, which we have 1, 2, 3, 4, 5, 6. But why are there 2 rings? Why aren't there 1 ring, or why aren't there 3 rings for that matter? So if you remember, and you should because we just learned about it, each of these corresponds to a block in terms of the electron configuration, right? So we have our S block here. This is going to be the D block. Oh, messed that up. We have our P block. Remember, helium's kind of not really part of that, but that's okay. And then it's not really shown here, but these would be our F. But obviously, it is not in this example. Okay? Well, think about, here's carbon. Well, here's carbon on the periodic table. Right? So back to here, this first row consists of what? It consists of just one S, and that can hold 2, right? So this first row can just hold, it has hydrogen, helium, which this has 1, this has 2, and we know the first ring holds 2, or the first orbital holds 2, so that's why, right? Carbon's first ring only holds 2 because that refers to our 1s. Next, we know we go here, which right here is our 2s, which can hold 2 again. And then this 2p, well, we need to just add 2 more to get to 6 electrons or 6 protons, right? So, well, there's your 2p2 right there and right there. So these first two refer to your 1s2. Some of these two refer to your 2s2, and then the other two refer to your 2p2. So when drawing Bohr models, that's how you want to think of your periodic table here. So I'm going to skip ahead a little bit to right here. Okay, and that's what this is saying. So one ring with two. So your first ring is going to have 2 maximum. Your second ring is going to hold 8 maximum. Your third ring is going to hold 8 maximum. Once we get to the fourth ring, you're going to be able to hold, well, let's see. We're going to have a 2s, right? You're going to have your 2s, which holds 2. And then you're going to have your, oh, actually, that's not 2s. That would be, sorry, 4s. I'm sorry. And then here, it's 3d10. And then here, you're going to get 4p6. So 2, 6, and then 10 is going to be 18. All right. So when we're doing Bohr models, that's how you want to think of these. Okay. So let's do some examples. I'll do some practice examples here. So helium. Okay. Where is it? That's my periodic table. Helium is just going to have 2. Well, it has 2, and we know it's just in this row, which refers to 1s. Okay. So we only have 1 ring, and we know we're going to have 2 electrons inside of there. So that's the Bohr model for helium. Calcium. Calcium is right here, and we know we have, this could get a little tricky, 1, 2, 3, 4 rings. All right. To draw, get a smaller pen here. All right, so we're gonna have 1. That is not very circular. 2, 3, and then 4. I made it. It's going to make it. So that first one is going to hold 2. Right? We know this one is going to hold 8 because we have the 2s. Well, we have the s orbital. We have the p. S can hold 2. The p can hold 6. 2 plus 6 is 8. So it's just going to evenly distribute those around here. Hopefully you guys can see that. 1, 2, 3, 4, 5, 6, 7, 8. This one will also hold 8. I'm just going to do it evenly, because that's how they would orient themselves in space. I think I missed one. 1, 2, 3, 4, 5, 6, 7, 8. Oh, no, I'm good. And then this one, well, where would we be out there? We would be right here. So we just need 2 more in this outer one. All right. I think you're kind of getting the picture there for the Bohr models. I don't want to bore you. Okay. Nah, I don't want to bore you. All right, so now let's go on to some Lewis structures. Okay. Look at that picture. Okay, so the thing is, in chemistry, all we really care about is the outside atom, or the outside atoms, the outside electrons. That's really where all of the magic, quote unquote, happens, where all the bonding takes place and all what dictates how that, maybe not entirely, but dictates, how it's going to bond with another element. Okay, so what the Lewis dot structure does is it boils the Bohr model down to just the outside electrons. See, we don't really care about these inner ones. They're not really dealing with, which isn't exactly true. They're not really dealing with the bonding on the outside. Okay, so carbon, which the Bohr model looks like this, all complicated, gets reduced down to just the symbol for the element, and then just the number of valence electrons represented by dots on the outside of the symbol. Okay, there's oxygen. Now, for these, it can get a little confusing. Not really for these. It can get a little confusing when we do bonding, but for the Lewis dot structure, you're really just focused on the outside electrons on the element. So, as an example, and I'll talk a little bit about the bonding. I probably won't do too much, but I'll talk a little bit about it. Okay, so to draw the Lewis model of each element, and I know I skipped over the other ones before, but we'll do all of them for this. We only care about our valence electrons. So for helium, if you remember our pattern of valence electrons, this row has 1, right? So we have 1, 2. We skip over here. If you want to find the valence electrons for these, remember you have to actually write out the electron configuration. This has 3 valence. This row has 4. This row has 5. This row has 6. This row has 7. And this row has 8, except for helium, which has 2. So helium has 2 electrons on it. And those are going to bond together. All right. For, what's our next one? Calcium, what do we have? 20. So we don't care about the 20 or 18 of those electrons. We just care about the outermost 2. And if you remember, where is it? Where do we have this? Yeah, right here. If you remember, calcium just has 2 on the outside, but also if you remember a little trick here, calcium's in our second row, so we know it just has 2 valence. So again, calcium has 2. Now I'm going to put it here this time. Okay, why? Well, it doesn't actually, I'm going to put this bigger, it doesn't actually matter, like, if it has 2, if you started out here or here or here, at all. So it doesn't matter where you put those. You generally want to be consistent, though. It makes more sense, but okay. And there's sodium. Well, there's the symbol for sodium. Sodium only has 1, so I'm going to put that, why not, over here. Okay. And that's the Lewis, those are the Lewis dot structures for various elements. Not too bad. However, bonding is a little different. So I know we're close to 13 minutes, so I'm going to try to wrap this up quickly. But for basic Lewis dot structure bonding, all you need to follow, and we're going to go over this in more detail later, but all you need to worry about is the octet rule right here. The octet rule means that elements, right here, well, yeah, right here, the octet rule. So, represent resulting structures that accommodate the octet rule. An element is surrounded by up to 8 dots, where element symbols represents the nucleus and dots represents the valence electron. So 8 dots represents having 8 electrons and therefore nice and stable like our noble gases, remember? Because those have the full s orbital and the full p orbital, so they're nice and very stable. I'm sorry you can't see that. Maybe you can see it better in this kind of lighting here. Okay, so I'm going to skip over some of this. Okay, I'm going to skip over some of this for now. And I'm going to do one of these on the next video, which is a practice video going over the homework, some of the homework, okay? So that'll explain a little bit of this. And remember, next week we will actually go over this in much more detail.